What if everything you think you know about the beginning of the universe is only half the story? Picture this: before stars, before galaxies, even before the fabric of space and time as we know it, the cosmos might have existed in a state so bizarre, so utterly counterintuitive, that it defies all our everyday logic. A state where reality itself was split into infinite possibilities, all existing at once. This isn't science fiction, it's the mind-bending frontier of quantum mechanics, and it could rewrite the very origin story of our universe. At the heart of this mystery lies one of quantum theory's most perplexing ideas: superposition. You've probably heard of Schrödinger's cat, that poor feline stuck in a box being both alive and dead at the same time. But what if the entire universe started that way? What if, in its earliest moments, reality itself was in a quantum superposition, a cosmic limbo where every possible outcome, every potential version of existence, flickered in and out of being simultaneously? It sounds impossible, yet some of the brightest minds in physics are seriously considering this as the key to understanding how everything began. In this journey, we're diving into 30 astonishing theories that explore this very idea. From the wild implications of a quantum birth for the cosmos to the lingering echoes of that primordial superposition hidden in the universe today, we'll unravel the clues that scientists are piecing together. Could the seeds of galaxies, the distribution of dark matter, even the arrow of time itself, all be traces of that first quantum leap into existence? Strap in, because we're about to explore a realm where the rules of reality as we know them don't just bend. They shatter, revealing a universe far stranger and more magnificent than we ever imagined. The very notion that our universe began with a single, definitive Big Bang might be one of the greatest oversimplifications in science. What if, instead of a clean, singular explosion, the birth of everything was a quantum storm of possibilities, an untamed sea of potential universes flickering in and out of existence all at once? This radical idea suggests the Big Bang wasn't a one-time event but rather a quantum superposition, where countless versions of creation overlapped in a primordial haze of uncertainty. Think of it like this: in the quantum world, particles don't settle on a single state until they're observed. An electron isn't just here or there, it's in all possible positions at once, a blur of probabilities waiting to collapse into reality. Now scale that up to the birth of the cosmos. What if space, time, even the laws of physics themselves existed in a fleeting, unresolved state, not one universe being born, but an infinite choir of possibilities singing in unison? Classical cosmology has long treated the Big Bang as the ultimate starting gun, a definitive moment where time and space burst into being. But quantum mechanics throws a wrench into that tidy narrative. If the universe began in a quantum superposition, then there was no single, clean beginning, just an unfathomable tangle of potentialities waiting to resolve. This means our entire cosmic history might just be one thread in a vast, tangled web of alternate realities that could have been. Some theorists suggest we might even find echoes of this quantum origin in the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in this ancient light could be the fingerprints of that primordial uncertainty, the leftover tremors from a reality that hadn't yet decided what it wanted to be. Even more mind-bending is the idea that this quantum superposition might not have fully collapsed. Some versions of the universe could still be branching away from ours, unseen and untouchable, like ghostly reflections in a cosmic hall of mirrors. If true, it means the Big Bang wasn't just the beginning of our story. It was the opening act of an infinite multiverse where every possibility played out somewhere. If the universe began in a quantum superposition where every possible outcome danced together in an unfathomable blur, then what happened to all those other possibilities? Did they simply vanish when our version of reality snapped into focus? Or here's where things get truly wild: did those untaken paths branch away, birthing parallel universes alongside our own? This isn't just speculation. It's a serious hypothesis grounded in one of quantum mechanics' most radical interpretations, the many worlds theory. Imagine tossing a quantum coin. In our world, it lands heads or tails, but according to many worlds, the moment that coin flips, reality splits: one universe where it's heads, another where it's tails. Now apply that to the birth of the cosmos. If the early universe existed in superposition, its collapse wouldn't have been a single, decisive event. Instead, every possible outcome, every potential configuration of particles, every variation of physical laws would have spawned its own separate timeline. Our universe, with its specific constants and conditions, would be just one leaf on an infinite, ever-growing tree of realities. This idea transforms the Big Bang from a solitary explosion into a cosmic fork in the road. What we call the beginning might have been more like a quantum dice roll, with universes bubbling into existence for every possible result. Somewhere out there, versions of reality could exist where gravity is stronger, where time runs backward, or where life took an entirely different shape. The cosmic microwave background's faint irregularities, those tiny wrinkles in space-time, might even hold clues like scars left behind when our universe peeled away from its siblings in that first moment of quantum separation. But here's the kicker: if many worlds is correct, those alternate universes aren't lost to history. They're still unfolding, invisible to us but just as real. Every quantum decision, from the spin of an electron to the fate of a star, continues to splinter reality into new branches. It's a dizzying thought that every choice you've ever made or didn't make exists somewhere in the multiverse. And it all traces back to that primordial superposition, a single quantum shiver that set infinite worlds into motion. The implications ripple even deeper. If other universes exist with different physical laws, ours might not be special, just statistically likely. We observe constants like the speed of light or the strength of gravity because they allow our existence. In universes where those numbers are off, there's no one around to notice. This anthropic principle adds another layer to the mystery, suggesting our entire reality could be one lucky draw in a quantum lottery with uncountable tickets. Yet for all its grandeur, the many worlds interpretation raises thorny questions. If every possibility plays out somewhere, how do we test it? Can we ever find evidence of these shadow universes? Some physicists speculate that gravitational waves or quantum entanglement might hold hints, subtle whispers from realities just beyond our reach. Others argue the theory is untestable by nature, a breathtaking idea forever trapped in the realm of thought experiments. But whether provable or not, this vision of a quantum-born multiverse reshapes our cosmic origin story. It paints the universe not as a singular, inevitable outcome, but as one thread in a vast, vibrating tapestry of realities, each born from that first, fragile moment when everything was possible. But what if the universe didn't just emerge from a quantum superposition? What if it sprang into existence from absolute nothingness? This is the audacious idea behind quantum fluctuations as genesis, a theory that suggests our entire reality might be the result of a random, microscopic blip in the void. Picture a vast, featureless emptiness: no space, no time, no particles, just pure nothingness. Yet even in that void, the rules of quantum mechanics whisper that something extraordinary can happen. At the heart of this idea lies Heisenberg's uncertainty principle, one of quantum theory's most fundamental laws. It states that on the tiniest scales, nature is inherently unpredictable. You can't precisely know both a particle's position and its momentum at the same time, but even more startling, this uncertainty means energy itself can appear and vanish in fleeting bursts, like bubbles forming in a cosmic foam. These aren't just mathematical quirks. In the right conditions, a quantum fluctuation could borrow enough energy from nowhere to create something from nothing. And if that something was dense and hot enough, it might just explode into an entire universe. Think of it like a cosmic version of static on an old television screen. Tiny flickers of randomness that, against all odds, coalesce into a coherent image. In this case, the static is the quantum vacuum seething with potential, and the image is everything we know. Some physicists argue that our universe could be one such flicker that, instead of fading away, stabilized and expanded into the cosmos we inhabit today. The implications are staggering. If true, it means reality didn't need a cause in the traditional sense. No divine spark, no collision of higher dimensional brains, just a random quantum event that, against incomprehensible odds, set the stage for galaxies, planets, and us. And if it happened once, why not countless times? This opens the door to an even wilder possibility. Our universe might just be one accidental creation in an endless sea of others, each born from its own fleeting quantum ripple. Yet for all its elegance, this theory isn't without its puzzles. How could a fluctuation so small scale up to an entire universe? And what about the eerie fine-tuning of our cosmos, the precise constants that allow life to exist? Some theorists propose that inflation, the universe's explosive early growth spurt, might bridge the gap, stretching a microscopic quantum event into a macroscopic reality. Others suggest that in the infinite randomness of quantum possibilities, a universe like ours was bound to emerge eventually, no matter how improbable. The real mind-bender is that this process might still be happening. If the quantum vacuum can birth one universe, why not more? Some models suggest new universes could be popping into existence right now, hidden in dimensions we can't perceive. Our entire reality might be just one bubble in an ever-expanding quantum froth, a single note in a symphony of spontaneous creation. This isn't just speculative philosophy. Scientists are actively searching for traces of these primordial quantum events. The distribution of galaxies, the faint echoes of gravitational waves, even the mysterious dark energy accelerating the universe's expansion, any of these could hold clues that we're living in a universe that once was, and perhaps still is, nothing more than a fleeting fluctuation that got lucky. Now let's take a sharp turn into one of the most head-spinning ideas in modern physics, the holographic principle. What if our three-dimensional universe, with all its galaxies, black holes, and swirling quantum fields, is nothing more than a projection of information stored on a two-dimensional surface at the edge of reality? It sounds like something ripped from a sci-fi movie, but this theory might hold the key to understanding how the universe's first quantum superposition imprinted itself onto the cosmos we see today. The holographic principle flips our intuition about reality on its head. Think of it like a credit card hologram, those shimmering images that seem to have depth when you tilt them, even though they're etched onto a flat surface. In the same way, physicists propose that all the information describing our 3D universe could be encoded on a distant, two-dimensional boundary, like data stamped onto the cosmic equivalent of a DVD. Every particle collision, every supernova explosion, every thought in your brain just flickering pixels on an unimaginably vast flat screen. So how does this tie back to the universe's first quantum superposition? Imagine that primordial state not as a blur of 3D possibilities, but as a fuzzy, fluctuating pattern etched onto a two-dimensional surface. The moment that superposition collapsed, it wasn't just choosing between versions of a 3D universe, it was selecting which hologram to project into existence. Our entire reality might be the cosmic equivalent of a film reel deciding which frame to display. This idea gains traction when you consider black holes. According to renowned physicist Leonard Susskind, the information swallowed by a black hole doesn't vanish, it gets smeared across its two-dimensional event horizon like cosmic spray paint. If black holes can encode 3D information on a 2D surface, why not the entire universe? Some theorists argue the Big Bang itself could have been a holographic boot-up. where quantum uncertainty on a boundary layer birthed the dimensions we experience. The implications are staggering. If true, the holographic principle would mean the universe's first superposition wasn't happening in the volume of space we imagine. It was playing out on a hidden, flat canvas. Those quantum fluctuations in the cosmic microwave background, just shadows of a deeper, two-dimensional code resolving itself. Even the arrow of time might emerge from how this cosmic projector sequences its frames. But here's where it gets even wilder. If our 3D world is a hologram, then quantum entanglement. That spooky connection between particles might just be threads stitching together distant points on the 2D surface. What we perceive as mysterious action at a distance could be simple neighborly interactions in the underlying code. This could explain why quantum mechanics feels so bizarre in 3 dimensions. We're literally reading the universe's source code in the wrong format. Critics argue the holographic principle is more mathematical poetry than testable science, but experiments are underway. Gravitational wave detectors might someday catch subtle pixelation in spacetime, like spotting the grain on a movie screen. Others hunt for anomalies in high-energy particle collisions that could reveal the universe's resolution limit. If either succeeds, it wouldn't just confirm a radical theory. It would mean we've glimpsed the flat, coded surface where reality's first quantum dice were rolled, and where every possible version of existence still lingers unseen. What if space itself isn't smooth and continuous, but built from tiny, indivisible building blocks, like pixels on a cosmic screen? This is the radical promise of loop quantum gravity, a theory that reimagines the fabric of reality as a shimmering web of interconnected spin networks. Unlike traditional physics, where space is an empty stage, loop quantum gravity suggests space is woven from threads of quantized gravity, each carrying a tiny packet of area or volume. And at the universe's birth, this web might have existed in a quantum superposition, vibrating with every possible configuration of spacetime at once. Picture a colossal tapestry, but instead of threads, it's made of microscopic loops, each one a quantum of space, humming with gravitational energy. These loops don't just sit still, they twist, link, and interact, creating a dynamic network that evolves over time. In this framework, the Big Bang wasn't an explosion in space. It was the explosive unfurling of space itself, as these quantum loops snapped into a particular pattern from a haze of overlapping possibilities. The real twist: spin networks don't just describe space, they are space. Every node in the network represents a tiny grain of reality, and every link between them encodes how these grains relate. In the early universe, before any measurement or observation, this network could have been a blur of superposed states with countless potential geometries coexisting. One moment, the cosmos might have resembled a knotted tangle, the next, a sprawling lattice. Only when this quantum foam collapsed did the universe we recognize, with its 3 dimensions and predictable physics, emerge. This idea turns classical cosmology on its head. Instead of matter and energy unfolding within spacetime, spacetime itself is the quantum actor, dancing to the tune of superposition and entanglement. Those primordial quantum jitters might still echo in today's universe, hidden in the large-scale structure of galaxies or the faint whispers of gravitational waves. Some researchers even speculate that black holes, where spacetime bends to its breaking point, could be windows into this deeper, granular nature of reality. But loop quantum gravity isn't just about rewriting the past. It could reshape our future understanding of physics. If space is quantized, there's no such thing as true emptiness, no infinite divisibility, no singularities where equations blow up. Even the Big Bang might give way to a big bounce, where a previous universe collapsed before rebounding into ours. And if spin networks hold the key, we might finally bridge the chasm between quantum mechanics and Einstein's gravity, uniting physics' greatest theories in a single, elegant framework. Yet for all its beauty, the theory faces daunting challenges. How do we test something so fundamentally tiny? Some experiments hunt for evidence in the cosmic microwave background, searching for imprints of spacetime's pixelation. Others probe high-energy particle collisions, hoping to spot gaps in the smoothness of reality. Until then, spin networks remain a breathtaking hypothesis, a reminder that the universe's first quantum moment might not have been a point, but a symphony of interwoven threads, vibrating with the untold potential of everything to come. What if time itself wasn't fundamental to the universe, just an illusion that emerged later, like frost forming on a window? This is the strange world painted by the Wheeler-DeWitt equation, one of physics' most provocative attempts to blend quantum mechanics with gravity. Unlike any other formula, it describes reality without mentioning time at all, as if the cosmic clock simply wasn't ticking when the universe first blinked into existence. At its core, this equation treats the entire cosmos like a single, timeless quantum object, a frozen moment where past, present, and future don't yet exist. Picture a cosmic photograph rather than a movie, capturing every possible configuration of matter and energy in one static snapshot. In this view, the Big Bang wasn't an event in time. It was a quantum superposition of all potential universes suspended in an eternal now. Only later, through some mechanism we don't fully understand, did time unfreeze, allowing history to unfold like a film reel finally set in motion. The implications rewrite our origin story completely. If the Wheeler-DeWitt equation is correct, the first quantum superposition wasn't fleeting or unstable. It was the default state of a reality where change hadn't yet been invented. Particles didn't move, waves didn't oscillate, entropy didn't increase, everything just was, caught in an infinite quantum pause. This challenges even our language. Words like before or after lose meaning in a framework where time doesn't exist. How then did our flowing, changing universe emerge? Some theorists propose that time is like temperature, a collective property that only appears when you zoom out. Just as a single water molecule isn't wet, perhaps individual quantum states aren't temporal until they entangle on a cosmic scale. Others suggest gravity played the role of timekeeper, breaking the perfect symmetry of the timeless state like a stone disturbing a pond's surface. The transition might have left echoes in the universe's large-scale structure, subtle correlations between galaxies that trace back to when time first switched on. The most radical interpretation comes from quantum cosmology, where observers themselves create time by making measurements. In this view, the universe began as a fog of possibilities that only took definite shape when something, perhaps an early quantum fluctuation, acted as the first observer, collapsing the superposition into a sequence of events we now call history. This would mean time isn't something the universe has, it's something the universe does when parts of it interact. Critics argue the Wheeler-DeWitt equation can't be the final word. After all, we experience time every second. Yet, even if incomplete, its vision of a timeless origin offers profound clues. If correct, the cosmic microwave background might contain fossilized imprints of that primordial stasis, like shadows in a cave reminding us that time itself had to be born. Future gravitational wave detectors could hunt for patterns matching a universe emerging from timelessness, while quantum computers might simulate how complexity arises from frozen initial states. Perhaps most mind-bending is the possibility that time's arrow isn't universal. Some regions of spacetime might still be stuck in that original timeless state, like cosmic glaciers where quantum superpositions never fully collapsed. Black holes could be portals to these zones, not just crushing matter, but freezing it outside time entirely. This suggests our universe might still be transitioning from its timeless beginnings, with time itself as the final, unfolding layer of reality's quantum origins. Roger Penrose's vision of the cosmos isn't just about beginnings, it's about endless rebirth. His conformal cyclic cosmology throws out the idea of a one-and-done Big Bang, proposing instead that our universe is just one act in an infinite cosmic play, each iteration called an eon. But here's where quantum mechanics takes center stage. At the threshold between these eons, when one universe fades to nothing and the next ignites, reality might dissolve back into a quantum superposition, a fleeting moment where every possible future cosmos flickers in unison before the next cycle snaps into place. Imagine the final moments of a dying universe stretched across eons. Stars burn out, black holes evaporate, and particles decay until only faint ripples of energy remain. In Penrose's framework, this sparse, cold expanse isn't the end. It's a cosmic reset button. As the universe expands to near infinite size, distances become meaningless. Space flattens, temperatures even out, and time loses its grip. At this conformal boundary, the distinction between end and beginning blurs. The universe's vast, empty twilight becomes mathematically identical to the hot, dense spark of a new Big Bang. In that transition, quantum mechanics could take the wheel, erasing the old universe's history and spawning a fresh superposition of possibilities. This cyclical rebirth isn't just poetic, it leaves fingerprints. Penrose and collaborators argue that collisions between supermassive black holes in past eons might have imprinted faint, circular patterns in the cosmic microwave background, like echoes of forgotten universes. These Hawking points, named after Stephen Hawking, would be ghostly remnants of black holes that evaporated long before our eon began. If detected, they'd be smoking gun evidence that our Big Bang was just one in an endless chain. The quantum twist: each reset might not preserve the same physical laws. One eon could emerge with gravity stronger or weaker, constants slightly tweaked, even dimensions rearranged. The superposition at the boundary wouldn't just reboot the universe, it'd reshuffle the cosmic deck. This means life-friendly conditions like ours might be rare jewels in an infinite necklace of eons, with most cycles too chaotic or barren to harbor complexity. Skeptics question how information could traverse these cosmic resets without violating thermodynamics, but Penrose suggests quantum entanglement might hold the key. Particles linked across eons could thread delicate patterns from one cycle to the next, like a secret handshake between universes. Others propose that dark matter, that enigmatic cosmic glue, might be debris from previous iterations, ash from a fire that burned before time. If Penrose is right, the quantum superposition we've been tracing back to the Big Bang wasn't a singular event. It's the universe's heartbeat, pulsing in the darkness between worlds. Each collapse into a new eon isn't an ending, but a cosmic sigh before the next breath. And somewhere in the unfathomable future, our universe's final particles might already be whispering the first quantum notes of another beginning. What if our act of looking backward toward the Big Bang is what ultimately made it happen? This isn't some philosophical thought experiment, it's the spine-tingling core of John Wheeler's participatory anthropic principle, a theory that flips causality on its head. Wheeler, the legendary physicist who coined the term black hole, proposed something even more radical, that conscious observers might not just study the universe but actively create it, retroactively shaping the very conditions that allowed us to exist. Picture this: in quantum mechanics, particles exist in fuzzy superpositions until measured. The act of observation forces them to choose a state. Wheeler took this further, suggesting the entire universe began in a quantum haze of possibilities, no definite laws, no fixed constants, until the first conscious beings evolved and looked back, collapsing that primordial superposition into a concrete history. In this view, the Big Bang didn't just lead to us, we, by observing it, caused it to happen the way it did. It's as if the universe was a question waiting for an answer, and we're the answer. This idea, sometimes called the observer-created universe, gains traction when you consider delayed choice experiments in quantum physics. In these lab setups, particles seem to decide their past behavior based on future measurements. Wheeler famously illustrated this with his cosmic scale version. Imagine light from a distant quasar bending around a galaxy, taking two possible paths to reach Earth. If we measure which path it took, we force it to have been a particle all along. But if we measure its wave-like interference pattern, we retroactively confirm it traveled both paths simultaneously. Now stretch this logic across billions of years. What if human astronomers, by choosing how to observe ancient light, are determining whether the early universe behaved as particles or waves? Critics argue this smacks of solipsism, placing too much importance on human consciousness. But Wheeler wasn't talking about individual minds magically shaping reality. He meant the universe's quantum possibilities only fully resolve into concrete history when information about them becomes irreversible, recorded in cosmic structures, absorbed by planets or processed by minds. In this framework, life isn't an accident, it's the universe's way of making itself real. The implications cascade like dominoes. If observation shapes cosmic history, our universe's life-friendly constants might not be lucky dice rolls, they're the inevitable result of observers existing to measure them. This solves the fine-tuning problem elegantly. Of course, the laws seem perfectly calibrated for life. Life is what crystallized them from the quantum foam. Even the arrow of time could emerge from this participatory act, with the future influencing the past in a subtle cosmic feedback loop, yet mysteries linger. Did earlier life forms, alien civilizations, primitive microbes contribute to collapsing the superposition before humans existed? Or was the universe's quantum fog only fully dispelled when self-aware observers arrived? Some models suggest black holes could act as primordial observers, their event horizons recording quantum data and etching history into space-time long before life emerged. Others propose the universe bootstrapped itself into existence through a chain of increasingly complex observers, each generation solidifying more of reality's scaffolding. Wheeler's vision blurs the line between physics and philosophy, but it's grounded in quantum theory's most stubborn paradoxes. Future experiments with quantum gravity or cosmic entanglement might reveal whether observation truly leaves marks on the universe's birth certificate. Until then, it offers a humbling perspective that in searching for our origins, we might be completing a cosmic circuit that began only when we turned our gaze backward, a universe awakening to itself through the eyes of its own creations. What if the universe's first quantum superposition wasn't a natural phenomenon at all, but the algorithmic foundation of a simulated reality? This is the electrifying intersection of the simulation hypothesis and quantum mechanics, where the blurry, probabilistic nature of our cosmos isn't a bug, it's the signature of a universe running on cosmic hardware. Think of quantum randomness as the procedural generation of reality, with every collapsed superposition just a line of code resolving in the simulation's processor. At the heart of this idea lies a striking parallel. In advanced video games, vast open worlds aren't stored in full detail. They're rendered on the fly using algorithms that generate landscapes only when a player looks. Quantum mechanics operates eerily similarly. Particles don't have definite properties until measured, almost like the universe is conserving computational resources by only calculating what's observed. The double-slit experiment, where particles behave as waves until measured, could be seen as optimization logic. Why render a particle's path if nobody's watching? Some theorists take this further, suggesting the Big Bang was the initial boot-up sequence, where the simulation loaded its core parameters in a quantum superposition. This blurry start state allowed the system to test countless configurations before settling on the stable physics we experience. Glitches in this process might explain cosmic anomalies like dark energy, unexpected variables left over from the universe's debugging phase. Even the speed of light could be a processing limit, the maximum clock speed of the cosmic CPU preventing the simulation from crashing. But here's where it gets meta. If our reality is a simulation, its creators might themselves exist in a simulated universe, nesting realities like cosmic matryoshka dolls. This raises a chilling possibility. Quantum indeterminacy could be intentional noise, a firewall preventing simulated beings from reverse engineering their own source code. Planck length, the smallest possible unit of space, might simply be the pixel size of the simulation's resolution. Critics argue this is unprovable metaphysics, but surprising clues might exist. Physicists have proposed looking for computational shortcuts in high-energy physics, certain energy levels where particle behavior becomes suspiciously simplified, like a game developer reducing detail in distant objects. Others suggest quantum entanglements faster than light linkage could be a networking trick, two objects secretly sharing memory addresses behind the scenes. Whether metaphor or literal truth, this framework reframes superposition as the universe's most elegant compression algorithm, a way to keep reality light enough to run. Every time a quantum dice roll settles, we might be glimpsing the cosmic engine humming beneath the surface, rendering existence one probability at a time. String theory paints a picture of reality so vast and intricate that the Big Bang might have been less an explosion and more like a cosmic menu, a dizzying array of possible universes flickering into existence all at once. At its core, string theory suggests that the fundamental building blocks of reality aren't point-like particles but tiny, vibrating strings, each oscillation pattern giving rise to different particles and forces. But here's the twist: these strings don't just vibrate in the 3 dimensions we know. They dance through a hidden tapestry of extra dimensions, curled up so tightly we've never detected them. And the way those dimensions fold and twist, that determines everything from the strength of gravity to the mass of an electron. This is where the landscape comes in, a mind-boggling collection of possible configurations for those extra dimensions, each representing a unique vacuum state with its own physics. Think of it like a cosmic game of musical chairs, where the music stopping means the universe picks one vacuum state to settle into. But in those first moments after the Big Bang, before any music stopped, the universe might have existed in a quantum superposition of all these possible configurations simultaneously, a shimmering, unstable foam where every law of physics, every constant of nature was up for grabs. Imagine a flickering light bulb trying to decide what color to be. Red, blue, green, each hue represents a different vacuum state, a different version of reality. Now replace that bulb with the entire cosmos and the colors with alternate laws of physics. That's the landscape of string theory. In this view, our universe isn't special. It's just one outcome in a near-infinite ensemble of possibilities, all competing for dominance in that first quantum instant. Some theorists argue this could explain the eerie fine-tuning of our cosmos. Why is the cosmological constant so perfectly calibrated to allow galaxies and life to form? In the string theory landscape, it's simple statistics. With enough vacuum states in superposition, some had to end up life-friendly by sheer chance. We're not in a designed universe, we're in the one lottery ticket that hit the jackpot, but the real shocker, this superposition might not be entirely in the past. The multiverse interpretation suggests other vacuum states could still exist beyond our cosmic horizon, like bubbles in an endless froth. Each bubble universe, with its own unique physics, might have crystallized from that primordial quantum haze, forever separated from us by inflationary expansion. Even now, the fabric of spacetime could be seething with alternative realities, their existence hinted at by faint anomalies in the cosmic microwave background or the distribution of dark matter. Critics point out the landscape's staggering complexity. Some estimates suggest 10 to the power of 500 possible vacuum states. Testing such a theory seems impossible, but clues might lurk in high-energy particle colliders or subtle gravitational waves. If string theory's landscape is real, then the universe's first quantum moment wasn't just a choice between paths, it was a simultaneous exploration of every possible road, with our reality just one winding lane in an endless cosmic highway. And somewhere out there, in the vastness of the multiverse, another version of you might be living in a world where gravity is stronger, time runs backward or the sky burns purple, proof that the universe's first superposition never truly collapsed but simply branched into infinity. The Boltzmann brain paradox takes the quantum weirdness of the early universe to its logical extreme, and the conclusion will unsettle even the most seasoned physicists. Picture this: in an infinite cosmos governed by entropy, random quantum fluctuations could, by sheer chance, spontaneously assemble a fully formed conscious brain, complete with false memories of an entire life, for just a fleeting moment before dissolving back into chaos. This eerie thought experiment, dreamed up by physicist Ludwig Boltzmann, doesn't just question the nature of reality, it suggests we might be those accidental minds hallucinating the universe itself. Now connect that to the universe's quantum origins. If the Big Bang emerged from a quantum superposition, a storm of possibilities where every potential state flickered in and out of existence, then Boltzmann brains become more than hypothetical. They could be inevitable. In that primordial quantum foam, countless configurations of matter and energy would have briefly coalesced, some stable enough to form galaxies and stars, others collapsing instantly into disorder. But here's the terrifying twist: statistically, it's far more probable for a single, self-aware fluctuation like a Boltzmann brain to pop into existence than an entire ordered universe. The math suggests we should be drowning in these phantom observers, each convinced they're living in a coherent world. So why does our reality feel so real? Critics argue this paradox exposes a flaw in our understanding of quantum mechanics or cosmology. Maybe the universe's initial conditions weren't random, and perhaps some deeper law weeded out the unstable fluctuations, leaving only durable realities like ours. Others propose that consciousness itself acts as a filter, ensuring only coherent experiences count. But the most radical solution, that superposition never fully collapsed. Our universe might still be entangled with those fleeting Boltzmann states, their ghostly whispers lingering at the edges of quantum uncertainty. Every time a particle behaves unpredictably, every time a quantum measurement defies logic, we could be glimpsing the cracks in reality, moments where the cosmic simulation struggles to reconcile our ordered world with the chaos it sprang from. This isn't just metaphysics. Experimentalists are probing quantum systems for signs of decoherence, the process that supposedly collapses superpositions into concrete reality. If gaps in this process exist, they might reveal pockets of unreliability in the fabric of existence. Meanwhile, cosmologists scan the cosmic microwave background for anomalies that could betray our universe's accidental origins. The irony is delicious. The very science we use to explore reality might one day confirm that reality is a mirage. Yet the Boltzmann paradox also offers strange comfort. If consciousness can emerge from quantum randomness, even briefly, then life isn't just a happy accident, it's a fundamental possibility written into the universe's code. Whether we're solid beings in a durable cosmos or flickering patterns in a quantum storm, the fact that we experience anything at all remains the deepest mystery of all. What if the universe didn't just collapse from a quantum superposition by chance, but through a kind of cosmic survival of the fittest? This is the provocative premise of quantum Darwinism, a theory that suggests the early universe's blur of possibilities didn't fade randomly. Instead, certain states thrived because they were stable, replicating their information like dominant genes in an evolutionary arena. Think of the newborn cosmos as a quantum laboratory, teeming with countless versions of reality, some where gravity repelled instead of attracted, others where atoms couldn't form. Most of these fragile states flickered out almost instantly, like soap bubbles popping in a storm. But a handful possessed the right quantum fitness, configurations robust enough to resist decoherence, their information imprinting onto the environment like footprints in wet concrete. These were the universes that stuck around, their physics etched into the fabric of existence simply because they could persist long enough to be observed. In this view, the laws we take for granted, the exact strength of nuclear forces, the precise charge of an electron, aren't the result of fine-tuning or luck. They're the winners of a billion-year tournament, the last quantum state standing after less stable alternatives crumbled into oblivion. It's as if the early cosmos ran countless experiments in parallel, and we're living in the one trial that didn't spontaneously self-destruct. The eerie parallel to biology runs deep. Just as natural selection favors organisms that replicate effectively, quantum Darwinism suggests reality itself evolved to propagate its information. When a photon strikes a dust particle or a quark interacts with a gluon, they're not just exchanging energy, they're broadcasting their quantum states to the environment, reinforcing their version of reality. Over time, these microscopic measurements add up, amplifying certain states while others fade like forgotten whispers. Critics argue this raises thorny questions: who or what plays the role of the observer in the early universe before any life or instruments existed? Proponents counter that observation doesn't require consciousness, just interaction. A single hydrogen atom bouncing off another could collapse their shared quantum haze into a definite state, beginning the chain reaction that led to classical reality. The echoes of this quantum evolution might still be detectable. If certain states were selected for their stability, the cosmic microwave background could harbor subtle asymmetries, preferred directions where decoherence happened slightly faster. Even the mysterious uniformity of the universe, long chalked up to inflation, might instead reflect the triumph of the most durable quantum configuration. Quantum Darwinism doesn't just reshape our origin story, it redefines reality itself as an ongoing process of selection, where every particle interaction is a vote for what gets to stay real. In this light, the universe isn't a static stage but a dynamic ecosystem, where the laws of physics are less like immutable commandments and more like living things shaped by the relentless pressure to endure. Imagine the universe as a hollow sphere with everything we see, galaxies, planets, even time itself, projected from information etched onto its inner surface. This isn't science fiction, it's the startling vision of the AD/CFT correspondence, a theoretical bridge between two seemingly unrelated realms of physics. On one side, you have string theory's playground, a hypothetical universe with unusual geometry called anti-de Sitter space, or AD-S. On the other, a quantum theory living on its boundary, known as a conformal field theory, or CFT. The radical claim, these two frameworks are mathematically equivalent flip sides of the same cosmic coin. This duality flips our intuition about reality inside out. Normally, we think of quantum weirdness happening within the universe, particles in superposition, entangled states collapsing when measured. But AD/CFT suggests the real action might be happening outside, on a distant boundary we can't perceive. In this view, the universe's first quantum superposition wasn't a property of the early cosmos itself. It was encoded in a quantum theory operating on its edges, like a holographic recipe generating three-dimensional reality from two-dimensional instructions. Picture a quantum computer the size of the cosmos, its qubits humming on the universe's perimeter. Every fluctuation in that boundary theory would manifest inside as particles, forces, even space-time itself. The Big Bang's quantum haze, just the boundary theory's calculations running hot, testing infinite configurations before settling into the stable universe we inhabit. This could explain why quantum mechanics feels so fundamental. It's not just the language of particles, but the native code of reality's source. The implications are staggering. If true, entanglement, that spooky connection between particles, might simply be threads stitching together distant points on the boundary, black holes. They could be cosmic error messages where the boundary theory's data gets scrambled. Even the arrow of time might emerge from how information flows across this hidden surface. Critics argue AD/CFT is a mathematical curiosity with no proven link to our real universe, which resembles de Sitter space, not anti-de Sitter, yet tantalizing clues suggest otherwise. The precision of AD/CFT's predictions about quantum gravity has stunned physicists, like stumbling onto a Rosetta Stone for spacetime. Some researchers even speculate our universe might be a defect in a higher dimensional AD space, its boundary physics leaking into our reality like ink through paper. If this correspondence holds, it would mean the universe's first quantum moment wasn't confined to a point in space. It was a seismic ripple across reality's edges, rewriting not just what exists, but where existence itself is computed. Black holes might be more than just cosmic vacuum cleaners. They could be holding onto secrets from the universe's very first moments. The quantum hair hypothesis, a radical new twist on black hole physics, suggests these gravitational monsters don't completely erase what falls inside. Instead, they leave faint quantum-scale traces like strands of cosmic DNA that encode information about their past. But here's where it gets mind-blowing. If black holes preserve quantum data today, could the universe itself have left similar imprints when it emerged from its primordial superposition? Imagine the early universe as a tangled knot of quantum possibilities. As it collapsed into one concrete reality, most of those overlapping states vanished, or so we thought. The quantum hair hypothesis hints that some of that information might have clung to spacetime itself, like fingerprints on a cosmic window. Black holes, with their ability to warp reality to its limits, could be the perfect places to look for these echoes. Their event horizons might not be the smooth, featureless membranes Einstein predicted, but textured with subtle quantum fluctuations, tiny hairs that whisper about the universe's birth. This idea flips the script on one of physics' biggest puzzles, the black hole information paradox. For decades, scientists argued whether anything could escape a black hole's grip. Hawking radiation suggested they evaporate over time, seemingly erasing all trace of what fell in. But quantum mechanics forbids such permanent loss. Information can't just vanish. The quantum hair proposal bridges this gap, suggesting that while black holes might scramble information, they don't destroy it entirely. Those faint quantum imprints could be the universe's way of keeping receipts even in the face of oblivion. Now stretch this back to the Big Bang. If black holes can preserve quantum data today, why couldn't the infant universe have done the same? The chaotic soup of particles and forces in those first moments might have left behind similar quantum hairs, subtle wrinkles in spacetime that carried forward traces of the superposition they emerged from. These wouldn't be fossils in the traditional sense. They'd be more like shadows, quantum echoes lingering in the fabric of reality itself. Some theorists speculate we might find these primordial signatures in gravitational waves, ripples from black hole collisions that could carry traces of quantum hair in their waveforms. Others suggest the cosmic microwave background, that ancient afterglow of the Big Bang, might hide patterns pointing back to the universe's quantum origins. Even dark matter, that mysterious cosmic glue, could be entangled with these early imprints, its behavior shaped by the same quantum rules that governed the first moments. But the most tantalizing possibility, if quantum hair exists, it could mean the universe never fully let go of its superposition roots. Some part of that original quantum blur might still be with us, woven into the very laws we take for granted. Every black hole, every particle collision, every flicker of starlight could be part of a cosmic conversation that began when reality itself was still deciding what it wanted to be. This isn't just about solving black hole mysteries, it's about rewriting our origin story. The quantum hair hypothesis doesn't just connect the dots between black holes and the Big Bang. It suggests the universe's first quantum moment wasn't a clean break, but a delicate unraveling one that left threads still dangling, waiting for us to pull. What if the universe's first quantum superposition wasn't just a blur of possibilities, but a wormhole, a bridge stitching together alternate versions of reality like threads in a cosmic tapestry? This is the extraordinary claim of the ER equals EPR conjecture, a theory that links two of physics' most mind-bending ideas, Einstein-Rosen bridges, the wormholes hidden in the equations of relativity, and quantum entanglement, that ghostly connection between particles. At its core, the proposal suggests entangled particles aren't just mysteriously linked, they're secretly joined by microscopic wormholes, tunnels through space-time so tiny they'd make a neutron look like a galaxy. Now scale that up to the Big Bang. If today's quantum entanglement creates space-time threads, could the universe's first superposition have been a quantum wormhole connecting every possible version of creation? Picture the infant cosmos not as a single point, but as a fractal web of wormholes, each throat branching to a different potential universe, each path a unique set of physical laws or initial conditions. In this view, the Big Bang wasn't an explosion in space, but the violent unraveling of this quantum wormhole network. As the superposition collapsed, most pathways pinched shut, leaving only our particular universe's thread to expand into the reality we know. The cosmic microwave background's delicate patterns might even bear scars from where other branches tore away, like fingerprints left on spacetime's doorframe. The elegance of this idea lies in how it solves two puzzles at once. First, it explains why quantum superposition feels so alien, because it's literally a topology of spacetime we can't perceive, like ants unaware they're crawling through a crumpled piece of paper. Second, it suggests the universe's spooky quantum connections entanglement aren't just correlations, but actual geometric structures. When two black holes entangle today, they might be recreating the universe's first act on a miniature scale, their event horizons joined by a wormhole just as the primordial cosmos was stitched together by quantum bridges. Some theorists take this further, proposing that dark matter, the invisible glue holding galaxies together, could be remnants of those collapsed wormhole threads, disconnected from our reality but still tugging on it gravitationally. Others speculate that quantum fluctuations in empty space are echoes of the original network's vibrations, spacetime's way of remembering its entangled birth. Even the arrow of time might emerge from this model. As the wormhole network decayed, it could have set causality in motion like dominoes falling in one irreversible direction. Yet the most radical implication is that superposition never truly ends. If ER equals EPR is correct, then every quantum decision, every collapsed wave function, might be a fork in a wormhole with alternate outcomes playing out in branches we can't access. This means the universe's first moment wasn't a clean break from possibility, but a fractal divergence with threads of reality still invisibly woven together at a quantum level. Black holes, those cosmic shredders of information, might be the key to testing this. If their interiors are secretly wormholes to other quantum states, their evaporation could leave behind telltale signatures in Hawking radiation. Future gravitational wave detectors might catch whispers of these quantum bridges when black holes merge, their events ringing spacetime like a bell struck from both inside and outside our universe. Until then, AR equals EPR offers a breathtaking vision that the universe didn't just begin in superposition, it began as a labyrinth, and we're living in the one path that led to us. Time doesn't just shape our reality, it might be the most baffling illusion the universe ever conjured. In quantum cosmology, the concept of time dissolves into something far stranger. If the universe began in a quantum superposition, a blur of all possible states, then time as we know it couldn't have existed at the start. There was no before, no ticking clock, just an unfathomable stillness where past, present, and future were one. This radical idea doesn't just rewrite the Big Bang, it erases the very idea of a beginning altogether. Think of it like a frozen lake. From above, the ice seems solid, unbroken, until a crack forms and suddenly motion appears where none existed. In the same way, time might not be fundamental to the cosmos but an emergent property, something that crystallized from quantum chaos as the universe cooled and settled into its current form. The Wheeler-DeWitt equation, a cornerstone of quantum gravity, describes reality without any reference to time at all, as if the cosmos were a single, unchanging quantum object, and the flow of time is just our limited way of perceiving it. This means the Big Bang wasn't an event in time, it was the moment time itself flickered into existence. So how did we get from timelessness to the ticking universe we know? One possibility lies in decoherence, the process that collapses quantum superpositions into definite states. As the early universe expanded and particles began interacting, their quantum fuzziness faded, leaving behind a world concrete enough to support cause and effect. In this view, time's arrow isn't written into the fabric of reality. It's a byproduct of increasing entropy, like a river flowing downhill simply because it's the most probable path. The past seems fixed because those quantum possibilities have already decohered, while the future remains open, still shimmering with uncertainty. This solves one of cosmology's greatest paradoxes, the question of what came before the Big Bang. If time emerged from a timeless state, then asking what happened before is like asking what's north of the North Pole. It's a question that loses all meaning. Some models suggest the universe could have transitioned from a static quantum realm into a dynamic classical one through a spontaneous symmetry breaking, similar to how water suddenly freezes into ice below 0 degrees. In that critical moment, the symmetry of timelessness shattered, and time began its irreversible march forward. The echoes of this transition might still be visible. If time emerged unevenly, certain regions of the universe could have crystallized faster than others, leaving faint anisotropies in the cosmic microwave background, subtle wrinkles in space-time where the clock started ticking at slightly different rates. Some theorists even propose that black holes could be pockets where time's emergence never completed, their event horizons marking the boundary between our temporal world and the timeless quantum foam from which it sprang. Yet the deepest implication is this: if time isn't fundamental, then our entire experience of reality is a kind of cosmic sleight of hand. The past isn't gone, it's just decohered, locked into place by countless quantum interactions. The future isn't unreal, it's a superposition we haven't observed yet, and the present a fleeting illusion, the knife edge where possibility becomes history. In this light, the universe's first quantum moment wasn't the start of time, it was the moment reality learned to tell itself a story. What if the Big Bang wasn't the beginning, just the universe's way of bouncing back from a cosmic collapse? The quantum bounce scenario paints a radically different origin story, one where our expanding cosmos was born from the ashes of a previous universe's death. Forget about a singular, mysterious starting point. This theory suggests space and time have been cycling through endless expansions and contractions like a cosmic accordion, with each bang preceded by a crunch. At the heart of this idea lies loop quantum gravity, which reimagines space-time not as smooth and continuous, but as a woven fabric of tiny, indivisible threads. When the previous universe reached its maximum density during collapse, these quantum threads didn't snap into a singularity, they rebounded. Picture a spring compressed to its limit. Just when it seems it can't squeeze further, it recoils with explosive force. In the quantum bounce model, the universe works the same way. That rebound, we call it the Big Bang, but it might really have been a big bounce, an echo of eternity rather than a true beginning. This solves one of cosmology's most vexing puzzles, the singularity problem. Classical physics breaks down when matter becomes infinitely dense, but a quantum bounce avoids that mathematical nightmare entirely. Instead of an unknowable point of infinite heat and density, the universe's history stretches backward through a prior phase of contraction, carrying traces of its past like cosmic memories encoded in space-time structure. Some researchers suggest these echoes might even be detectable in the cosmic microwave background, subtle swirls in the ancient light that hint at a universe before ours. The implications cascade outward. If the cycle continues, our expanding universe could one day reverse course, galaxies drawing together like marbles rolling uphill until the next bounce occurs. But here's the twist: each cycle might not be an identical replay. Quantum fluctuations during the bounce could tweak the fundamental constants slightly, meaning every iteration could have different physics, different particles, even different dimensions. Our universe's life-permitting precision might just be a lucky roll of quantum dice across countless cycles. Critics argue we lack evidence for a pre-Big Bang phase, but proponents counter that the bounce would have reset most traces. Still, subtle fingerprints might remain. Certain gravitational wave patterns or anomalies in large-scale galaxy distribution could betray our universe's cyclic heritage. Future experiments might even uncover relics particles or topological defects that slipped through the bounce unscathed, cosmic refugees from a universe long gone. This vision transforms the cosmos from a one-and-done creation into an immortal phoenix forever rising from its own ashes. Time loses its arrow, stretched across cycles without end or beginning. And us, we might be momentary sparks in an infinite dance of collapse and rebirth, living proof that even universes can learn to bounce back. What if consciousness didn't just emerge from the universe? What if it created it? This is the staggering claim of the observer-driven Big Bang, a theory that takes the von Neumann-Wigner interpretation of quantum mechanics to its ultimate extreme. In this radical vision, the universe didn't simply collapse from its primordial quantum superposition due to random chance or environmental noise. Instead, the presence of conscious observers, whether human minds, alien intelligences, or some deeper form of cosmic awareness, acted as the catalyst that solidified reality into existence. At the heart of this idea lies one of quantum theory's most contentious debates, the measurement problem. In the lab, particles exist in fuzzy superpositions until measured, at which point they snap into definite states. The von Neumann-Wigner interpretation suggests this collapse isn't caused by detectors or interaction with the environment, it's triggered by consciousness itself. Scale this up to cosmology, and you arrive at a jaw-dropping possibility. The Big Bang's quantum haze might have lingered indefinitely until the first glimmers of awareness emerged to observe it, retroactively sealing the universe's initial conditions. Think of it like a cosmic version of the double-slit experiment. In the lab, photons behave as waves when unobserved but collapse into particles when measured. Now imagine the early universe as a wave function spanning every possible configuration, an infinite cosmic slit, where reality hadn't yet chosen its form. The moment a conscious observer appeared, whether billions of years later, it could have reached back through time like a quantum echo, collapsing the superposition into a single classical universe. This would mean the Big Bang wasn't an independent event. It was a response to the eventual arrival of observers who would one day look back and ask, how did this all begin? The implications unravel like a fractal. If consciousness collapses quantum states, then the universe's fine-tuning isn't a lucky accident, it's inevitable. Only a cosmos capable of birthing observers could ever achieve definite reality, explaining why the constants of nature seem perfectly calibrated for life. Even the arrow of time gains new meaning. Causality might flow both forward and backward, with future observers influencing the past through a phenomenon called retrocausality. Critics argue this veers into metaphysics, but tantalizing clues exist. Delayed choice experiments show particles behaving as if they know how they'll be measured in the future. Quantum entanglement's spooky action at a distance could hint at a universe where observation stitches together space and time. And if consciousness truly drives collapse, then black holes, where information vanishes from observation, might be regions where reality unravels back into quantum potential. This isn't just about humans. Any self-referential system complex enough to observe its environment could play this role, from advanced civilizations to hypothetical quantum structures in the early universe. Perhaps the cosmos bootstrapped itself into existence through layers of emergent observation. each wave function collapse, building toward more complex observers who would further sharpen reality's focus. The most haunting question remains: if consciousness shapes reality, what happens when we stop looking? Does the universe dissolve back into possibility like a dream upon waking? Or do the imprints of observation endure, etched into space-time like cosmic footsteps in the sand? Whether testable or not, this theory forces us to confront a profound truth. In asking how the universe began, we might have become part of the answer. Most of us take space for granted, a smooth, featureless stage where everything plays out. But what if, in the universe's first moments, space itself was nothing like we know it? The quantum gravity model throws out everything we assume about the fabric of reality, proposing that space wasn't always continuous. Instead, it might have started as a chaotic, ever-changing graph, a cosmic connect-the-dots where points of reality were stitched together by links that flickered in and out of existence. Picture an unimaginably hot, dense early universe not as a void, but as a seething network of nodes and connections, like a hyper-dimensional spiderweb. Each node represented a potential location, and the links between them dictated how information could travel. But here's the twist: in this primordial state, the connections weren't fixed. Some links were strong, others weak. Some points were highly connected, while others barely touched the rest of the web. This wasn't space as we know it, it was more like a quantum soup where geometry itself was undecided. A roiling superposition of every possible way points could be arranged. As the universe cooled, this quantum graph might have undergone a dramatic phase transition like water, freezing into ice or a magnet aligning its poles. The chaotic web snapped into a stable, ordered lattice with nodes linking in predictable, repeating patterns. These patterns could have formed the basis of the three-dimensional grid we now perceive as space. The links that once flickered probabilistically became rigid and uniform, giving rise to the consistent speed of light, the fixed dimensions we move through, and even the very notion of distance itself. This phase transition wouldn't have been perfect. Just as ice forms with tiny cracks and defects, spaces freezing might have left behind imperfections, cosmic cracks in the fabric of reality. Some theorists speculate that these defects could explain dark energy, those mysterious voids where space itself seems to repel rather than attract. Others suggest that black holes might be tangled knots in the gravity, regions where the lattice of space frays or tears. Even the speed of light could be a side effect, a cosmic speed limit set by how quickly information can hop from node to node in the frozen graph. The quantum gravity model doesn't just reshape our past, it could redefine the future of physics. If space really is a lattice, then at extremely tiny scales, our smooth, continuous universe should break down into pixels. This would mean there's a shortest possible distance, a smallest unit of space itself. Some experiments hunting for quantum gravity hints, like anomalies in high-energy particle collisions or distortions in gamma-ray bursts, might already be glimpsing this granularity. But the most haunting implication: if the universe's geometry emerged from a quantum graph, then superposition wasn't just a property of particles, it was the very nature of reality. Before space chose its structure, every possible configuration existed at once. We're not living in the only version of space, just the one that froze into place. Somewhere out there, in the untouchable reaches of quantum potential, alternate geometries might still linger like ghostly blueprints for realities that never were. This isn't just abstract math. If quantum gravity is real, then the universe's first moment wasn't a bang, it was a cosmic chill, the instant when infinite possibilities crystallized into the stage we now call home. And if we look closely enough, the echoes of that transition might still be written in the way light travels, the way gravity bends, and the way space itself stubbornly refuses to let us see the seams. The Higgs field is often called the universe's cosmic molasses, the invisible treacle that gives particles their mass and shapes the very laws of physics. But what if its defining feature, its strength, wasn't always set in stone? Imagine a newborn cosmos where the Higgs field wasn't a fixed value but a flickering quantum possibility, oscillating between every possible strength simultaneously. In this radical scenario, the early universe didn't just have one set of physical laws, it contained all possible versions of them, each tied to a different Higgs value, all coexisting in a dizzying quantum blur. At the heart of this theory lies a startling parallel to how particles behave in the lab. Just as an electron spins both clockwise and counterclockwise until measured, the Higgs field could have existed in a superposition of all possible energy states. Some configurations would have made particles impossibly heavy, others impossibly light. Atoms might not have formed in some branches of this quantum haze, while in others gravity could have been too weak to pull matter together. The cosmos we know emerged only when this superposition collapsed, when decoherence chose one Higgs value from the infinite menu, locking in the masses of particles and the rules they play by. The mechanism behind this collapse might be etched into the universe's oldest light. Tiny variations in the cosmic microwave background, those faint temperature differences that seeded galaxy formation, could be quantum fingerprints, imprints of the moment the Higgs field superposition resolved. Some theorists suggest these patterns aren't random but encode the choice our universe made between possible physics. Even more intriguing, the Higgs value we observe seems improbably balanced, too weak to collapse the universe into a black hole, too strong to prevent atoms from forming. In the quantum origins framework, this isn't luck, it's statistical inevitability. Countless other Higgs values existed in superposition, but only those permitting complexity persisted long enough to be observed. This idea reshapes our understanding of fundamental forces. If the Higgs field was once quantum uncertain, then electromagnetism and the nuclear forces might have been too, their strengths fluctuating until decoherence locked them in sync. The universe's perfect calibration for life wouldn't require divine fine-tuning, just quantum statistics. We don't live in a special cosmos. We live in the one that survived the collapse, where the dice landed in the narrow zone allowing stars, planets, and minds. Future particle colliders might test this by hunting for relics of that primordial uncertainty. Some models predict exotic particles frozen out when the Higgs field crystallized, like cosmic leftovers from a quantum feast. Others suggest gravitational waves from the early universe could carry echoes of the decoherence event, a faint tremor from when reality's rules snapped into focus. Whether proven or not, this vision transforms the Higgs from a static backdrop into an active participant in cosmic history, a quantum chameleon that, by settling into one identity, gave the universe its shape. Causal set theory offers a radical way to rethink the birth of the cosmos, not as a smooth unfolding of space and time, but as a flickering quantum game of connect the dots played on the tiniest possible scale. Imagine the early universe not as a seething plasma or a singularity, but as a sparse, churning sea of discrete events with no fixed order, no geometry, not even a clear past or future. Each event represented a potential moment of reality, like grains of sand tossed in a storm, waiting to settle into something meaningful. At the heart of this theory lies a simple but profound idea. Before space-time existed as we know it, the universe was just a collection of these elemental events connected by causal relationships, bare bones links marking which events could influence others. Picture a vast, shifting network where points sporadically flash into existence, some briefly linking before dissolving back into the void. This wasn't space or time yet. It was the raw scaffolding from which they would later emerge, a quantum superposition of every possible causal structure, each fighting for permanence. The magic happens when quantum mechanics enters the picture. In those first chaotic moments, causal sets wouldn't have had a definite structure. Instead, they'd exist in a haze of probability, with every potential connection between events fluctuating wildly. One instant, event A might causally precede event B. The next, that relationship could reverse or vanish entirely. It's as if the universe was endlessly shuffling a deck of cosmic cards, trying out every possible sequence before settling on one. Only when this quantum foam of possibilities decohered, when probabilities collapsed into concrete relationships, did something resembling orderly spacetime crystallize. This transition from quantum chaos to classical causality could explain some of the universe's deepest mysteries. The apparent smoothness of space on large scales might just be an illusion, the way a handful of sand feels soft despite being made of gritty grains. Even the speed of light, that ultimate cosmic speed limit, could arise from how quickly information hops between linked events in the causal set's lattice. And the arrow of time, that might simply be the direction in which these cause and effect chains happen to stabilize, like fallen dominoes frozen mid-cascade. Some theorists speculate we might still find traces of this quantum causal soup in the large-scale structure of the universe. Subtle anomalies in how galaxies cluster or gravitational waves propagate could betray the granular, probabilistic roots of reality. Others suggest black holes, where causality breaks down entirely, might be windows into the universe's pre-geometric past, regions where the causal set briefly unravels back into quantum uncertainty. The most startling implication is that space-time itself could still be fundamentally discrete, like a digital image masquerading as a smooth photograph. If true, there's a smallest possible unit of time and space, a pixelation so fine we've yet to detect it. Future experiments hunting for quantum gravity effects, like tiny fluctuations in the spin of distant particles, might finally reveal these hidden pixels, proving that what we perceive as an endless cosmic stage is really a meticulously stitched tapestry woven from quantum threads. Causal set theory doesn't just rewrite the universe's origin story, it turns reality into a cosmic afterthought, an emergent property of something far stranger. The Big Bang wasn't an explosion in space, it was the moment an infinite quantum storm of maybe finally chose to become now, and every tick of the clock since has been an echo of that first fleeting decision. David Bohm's implicate order theory paints reality as a cosmic origami, an endless folding and unfolding of deeper layers we can barely glimpse. Imagine the early universe not as a chaotic explosion, but as an infinite sheet of paper intricately creased in ways that conceal its true nature. In this view, the quantum superposition at the dawn of time wasn't just a blur of possibilities, it was the implicate order itself. A hidden dimension where all potential states of reality existed as enfolded harmonies, waiting to be teased apart into the world we recognize. Bohm argued that what we perceive as the tangible universe, the explicate order, is just the unfolded projection of something far more fundamental. At the quantum level, particles aren't isolated objects but ripple-like expressions of this deeper reality, their behavior governed by a pilot wave of information flowing from the implicate realm. Translate this to cosmology, and the Big Bang becomes less like a beginning and more like the first great unfolding, a moment when the implicate order's infinite potentials began to unfurl into space-time matter and the laws we take for granted. This reshapes our understanding of superposition. Rather than particles existing in multiple states simultaneously, Bohm's framework suggests those states were always connected in the implicate order, like notes in a chord we couldn't yet hear. When the universe collapsed into classical reality, it wasn't choosing between options, it was revealing one thread of a vast, pre-existing tapestry. The cosmic microwave background's patterns might not be random fluctuations, but holographic imprints of that unfolding, shadows cast by the implicate order's hidden geometry. The eerie beauty of this idea lies in how it solves quantum entanglement's spooky action at a distance. If two particles instantly influence each other across light years, it's not magic, it's proof they were never truly separate in the implicate order, just differently folded aspects of the same underlying unity. Black holes might be cosmic creases where reality folds back inward, their event horizons stitching the explicate and implicate together like seams in a fabric. Even dark energy could emerge from tensions in this folding, the implicate order straining against the constraints of our unfolded reality. Critics dismiss the implicate order as untestable poetry, but modern physics keeps stumbling into Bohm-like ideas. Quantum gravity researchers now speak of spacetime as emergent, holographic theories posit hidden dimensions, and even quantum computers exploit non-local connections that resemble Bohm's pilot waves. Future experiments probing quantum decoherence or the nature of vacuum energy might reveal whispers of this deeper order, subtle fingerprints left when the universe transitioned from folded potential to tangible fact. Bohm's vision offers more than a new origin story. It suggests superposition was never a transient state, but a window into reality's true architecture. The universe didn't leave quantum weirdness behind after the Big Bang. It simply folded most of it out of sight, leaving us to puzzle over the creases. What if the universe's first quantum superposition wasn't about physics at all, but about information and belief? Quantum Bayesianism, or cubism, throws out the traditional rulebook by suggesting quantum states aren't objective features of reality, but subjective probabilities like betting odds in a cosmic casino. In this radical reframing, the early universe didn't exist in a superposition because particles were genuinely undecided. It was simply that no observer had yet placed their bets. Picture a deck of cards shuffled face down. Before you look, every possible arrangement exists as a probability in your mind. The moment you turn over the cards, your knowledge updates, collapsing those possibilities into one concrete sequence. Cubism applies this logic to quantum mechanics. The newborn cosmos wasn't a blur of actualized states, it was an infinite array of potentialities waiting to be resolved through interaction and observation. When we say the universe was in superposition, we're really saying it was a perfect blank slate of unupdated Bayesian probabilities. This turns the measurement problem inside out. Instead of wave functions collapsing due to some mysterious physical process, cubism argues collapse happens in the mind of the observer. Not in some mystical sense, but through the cold math of Bayesian inference, where probabilities get revised as new data comes in. Scale this up to cosmology, and the Big Bang's quantum haze becomes less a physical condition and more a description of maximum uncertainty. The first particles, the first forces, even spacetime itself gained definite properties not because of an external measurement, but because the universe's earliest observers, whether particles interacting or quantum fields decohering, updated their beliefs about what was real. The implications shake the foundations of physics. If cubism is correct, the fine-tuning of cosmic constants might reflect an inevitable statistical outcome, the universe's version of a gambler eventually settling on reliable odds after enough rounds. The arrow of time could emerge from the irreversible flow of information updates, like a cosmic croupier dealing cards in one direction. Even entanglements, spooky connections might just be correlations in a grand probability network, where separated particles aren't communicating but simply sharing consistent Bayesian priors. Critics argue this veers into solipsism, but cubists counter that it's profoundly empirical. It treats quantum mechanics as a tool for prediction, not a description of hidden reality. Future experiments probing quantum decoherence might reveal whether observation truly behaves like Bayesian updating at microscopic scales. Until then, this perspective offers a startling vision that the universe's first moment wasn't a physical event, but a mathematical breath, a hesitation before the first cosmic bet was placed, when anything was still possible and nothing yet known. Most of us experience time as an unshakable truth, a river flowing in one direction, carrying everything from the Big Bang to this very moment. But what if time isn't fundamental at all? The thermal time hypothesis throws a wrench into our most basic assumptions, proposing that time isn't woven into the fabric of reality. It's an illusion crafted by statistics and heat. Imagine the early universe not as a ticking clock, but as a cosmic casino where the roll of quantum dice didn't just determine what happened, but when things appeared to happen. Here's the radical core of this idea. Time emerges from entropy, the natural tendency of systems to become more disordered. Think of a cup of coffee cooling in a room. It's not some innate property of time making the heat disperse, but the statistical inevitability that energy spreads out. In the thermal time framework, the entire universe operates on this principle. The arrow of time isn't an intrinsic feature of space, it's a side effect of the universe's scramble toward equilibrium. Now apply this to the universe's quantum origins. If time is an emergent property, then the primordial superposition wasn't just a blur of possible states, it was a state where time itself hadn't yet crystallized. Without entropy gradients to create the illusion of past and future, the early cosmos existed in a kind of statistical limbo, a realm where cause and effect were still tangled in quantum potential. Only as particles interacted, as energy began to disperse unevenly, did the universe choose a direction for time's arrow, not because of some fundamental law, but because statistics favored it. This reframes the Big Bang's quantum haze in a startling new light. The superposition wasn't just about what the universe was, it was about when it could be. Some branches of that quantum foam might have briefly flirted with time flowing backward, others with time looping in knots, but the version that persisted, the one we inhabit, was the path where entropy's rise carved out a stable groove for causality to unfold. The cosmic microwave background's subtle imperfections might not just be density variations. They could be fossilized imprints of that first statistical tipping point, the moment randomness conspired to create the illusion of time. Critics argue that reducing time to thermodynamics feels like explaining a symphony by counting sound waves, but the math holds surprising power. Black holes, those cosmic wrecking balls of spacetime, might be the ultimate test. Near their event horizons, time distorts in ways that align eerily with thermal time's predictions, as if the universe is reminding us that time's flow is negotiable. Even quantum entanglements, instantaneous connections, make more sense if time is just a local phenomenon, a rule that doesn't apply behind the curtain. The most haunting implication: if time is statistical, then the universe's first superposition never truly ended. Somewhere beneath the surface of our orderly, time-bound reality, the quantum dice might still be rolling, whispering that every tick of the clock is just a particularly persuasive illusion. Beneath the smooth expanse of space we see lies a hidden storm, a seething, frothing chaos at scales so small they defy imagination. This is space-time foam, the turbulent quantum structure theorized to exist at the Planck length, where the fabric of reality churns like an ocean in a hurricane. If this frenzied foam is real, it might not just be a quirk of quantum gravity, it could be the last surviving whisper of the universe's first moments, when all of existence was a boiling quantum soup without form or order. At the Planck scale, a distance so tiny that a single atom seems gargantuan in comparison, space and time lose their familiar smoothness. Instead, they twist into fleeting bubbles of geometry that pop in and out of existence, forming a fractal foam of wormholes, quantum tunnels, and microscopic black holes. These structures aren't stable, they're ephemeral, flickering in trillionths of a second before vanishing back into the void. Yet collectively, they create a foam-like structure that underpins reality itself. Now rewind to the Big Bang. In those first unfathomable instants, the universe wasn't just hot and dense, it was a quantum maelstrom where space-time hadn't yet settled into a stable framework. Space, time, even causality rippled and fluctuated like waves in a storm. This primordial turbulence didn't just vanish when the cosmos cooled. Instead, it might have left behind scars, tiny, eternal eddies frozen into the foundation of reality. The space-time foam we theorize today could be those scars, the quantum equivalent of wrinkles in an ancient sheet of parchment, preserving the chaos of creation. This idea flips our understanding of quantum gravity. Instead of seeing space-time foam as an accidental byproduct of extreme physics, it becomes a cosmic fossil, a relic of the universe's earliest quantum superposition. Just as ice crystals form in branching patterns that echo the temperature swings of a winter storm, the foam's structure could encode the wild fluctuations of the Big Bang. The micro-wormholes and quantum bubbles might be like ancient cave paintings, telling the story of a time when reality itself was undecided. Some theories suggest these Planck-scale fluctuations could even influence the large-scale universe. Just as tiny vibrations in a spiderweb can travel to distant strands, quantum foam's turbulence might have seeded the faint irregularities in the cosmic microwave background, the same wrinkles that later grew into galaxies and galaxy clusters. If true, the vast cosmic web we see today could trace its origins to spacetime's primordial froth, stretching quantum fingerprints across billions of light years. Detecting this foam directly is impossible with current technology. Its scale is trillions of times smaller than anything we can probe. But indirect evidence might lurk in the behavior of high-energy cosmic rays or subtle distortions in light from distant quasars. Some models even predict that if space-time foam is real, it would slightly scramble the arrival times of photons traveling across the universe, like a hall of mirrors at the quantum scale. Future observatories like ultra-precise gravitational wave detectors or quantum gravity-sensitive telescopes might one day catch these whispers from the foam. The most profound implication: if spacetime foam truly is a remnant of the universe's quantum origins, then superposition never fully ended. At the deepest level, reality might still be trembling with uncertainty, its surface calm belying a storm beneath. Every tick of the clock, every measured distance could be an average, a statistical smoothing over of an infinite number of quantum fluctuations, each a tiny echo of creation's first chaotic breath. This vision transforms the cosmos from a static stage into a living, seething entity. The foam isn't just a curiosity of quantum gravity, it's a bridge to the dawn of time, a reminder that beneath the order we take for granted, the universe never forgot how to dance. Supersymmetry, one of the most elegant ideas in theoretical physics, suggests that every particle we know has a hidden twin, a shadowy counterpart vibrating at higher energies. But what if these twins weren't just exotic predictions? What if they were the key to understanding the universe's first quantum moment? Deep in the equations of supersymmetry lies a tantalizing possibility that the unbroken, pristine phase of this theory wasn't just a fleeting state. It was the universe's original superposition, a symmetrical blur where particles and their superpartners existed as undifferentiated possibilities, neither one nor the other, but both at once. In this vision, the early cosmos wasn't just a hot soup of quarks and photons. It was a realm of perfect balance, where matter and force-carrying particles were mirrored by their superpartners in a delicate cosmic dance. Electrons had selectrons, quarks had squarks, and even the force-carrying bosons had fermionic twins. The universe, in its purest form, was a superposition of all these identities simultaneously, its quantum state shimmering with potential. But this harmony couldn't last. As the cosmos cooled, supersymmetry broke like ice cracking under pressure, and that fracture forced reality to choose. The once symmetrical quantum haze collapsed into the lopsided universe we know today, where particles dominate and their superpartners, if they exist at all, hide at energies we've yet to probe. The echoes of this breaking might still reverberate through the cosmos. The Higgs boson's puzzlingly low mass, dark matter's ghostly presence, even the fact that gravity is absurdly weaker than the other forces, all could be scars from the moment supersymmetry shattered, locking the universe into one path of its original quantum superposition. Some theorists suggest that the very structure of spacetime could bear the marks of this transition. Quantum fluctuations frozen into the cosmic microwave background, might encode the tremors of that primordial symmetry breaking, like cosmic hieroglyphs telling the story of a time when reality hadn't yet decided what it would become. But the most radical implication, if supersymmetry's unbroken phase was the universe's first superposition, then the act of observation, the process that collapses quantum states, might not be a human-centric phenomenon, but a fundamental feature woven into the fabric of reality. Symmetry breaking wasn't just a passive cooling, it was a cosmic measurement, a moment when the universe observed itself and chose a side. Somewhere in the math, the equations might still hint at the roads not taken, the alternate universes where supersymmetry broke differently, leaving behind worlds where photons have mass or gravity operates in extra dimensions. Critics argue that supersymmetry's absence in current particle colliders casts doubt on this theory, but proponents counter that we might be looking for the wrong remnants. Instead of hunting for superparticles directly, we should search for their echoes, subtle imbalances in the universe's expansion, anomalies in high-energy cosmic rays, or even relics from the phase transition itself, lurking in the quantum vacuum like bubbles in a cosmic champagne flute. If this vision holds, then the universe we inhabit isn't the only possible outcome, it's just the one where supersymmetry broke in a way that allowed galaxies, stars, and life to form. The others, they might still exist as ghostly quantum branches, forever hovering at the edge of reality, reminding us that the cosmos was once a place where every particle had a twin, and nothing was yet set in stone. What if the universe isn't made of matter or energy at all, but of something far more fundamental, information? Quantum information theory takes the mind-bending principles of superposition and asks us to imagine reality as the ultimate cosmic hard drive, where every particle, every force, even space-time itself is just a pattern of encoded data. In this framework, the universe's first quantum superposition wasn't a chaotic explosion of possibilities. It was the system booting up, loading every potential state of existence into its memory before executing the program we call reality. Think of it like a quantum computer running the ultimate simulation. Unlike classical bits that are either 0 or 1, quantum bits or qubits can exist in both states simultaneously, a blur of probabilities waiting to collapse into definite answers. Now scale that up to the Big Bang. Instead of a singularity of infinite density, picture a cosmic processor initializing its registers with every possible configuration of particles, forces, and physical laws stored in superposition. The moment this quantum hard drive decoded, selecting one set of parameters over others, the universe as we know it began executing its code. This idea transforms how we interpret the universe's fine-tuning. The precise constants allowing atoms, stars, and life aren't accidents, they're the stable configurations in a vast computational landscape. Just as a laptop crashes if its memory corrupts, most quantum states in the early universe would have been unstable, collapsing instantly. Only the self-consistent patterns, the ones capable of sustaining complexity, persisted long enough to form galaxies and minds. The cosmic microwave background's intricate fluctuations. They might not be random noise, but the universe's way of defragmenting its drive, organizing quantum data into structures durable enough to last billions of years. The parallels to modern computing run deep. Black holes could be nature's garbage collectors, their event horizons acting as firewalls that scramble information into thermal noise, cosmic equivalents of secure data wipes. Entanglement, that spooky connection between particles, might simply be quantum error correction, nature's method of preserving coherence across vast distances. Even dark energy's mysterious push could reflect the universe's growing computational overhead, its memory expanding as it processes more information over time. But here's the twist: if reality is fundamentally informational, then superposition never truly ends. The universe isn't a fixed output, it's an ongoing computation with every interaction updating its state. When you observe a particle, you're not just collapsing its wave function, you're querying the cosmic database, forcing it to retrieve a value. The double-slit experiment's infamous observer effect becomes less a paradox and more a feature of the system, a reminder that reality renders only what's being observed, like a video game optimizing graphics for the player's current view. Critics argue this veers into digital physics, a controversial cousin of string theory, but supporting clues abound. The holographic principle suggests the universe's information content scales with surface area, not volume, just like a hard drive's storage limits. Quantum gravity researchers find entropy a measure of information deeply woven into spacetime's fabric. Even the Planck length, the smallest meaningful distance, could represent the pixel size of reality's resolution, the ultimate limit of its rendering power. Perhaps most startling is the implication that the Big Bang wasn't a physical event, but a logical one the instant the cosmic OS switched from idle to runtime. If true, then the universe's first quantum moment wasn't the beginning of something material, but the initialization of a process. We're not just made of stardust, we're patterns in the grandest computation of all, living proofs that information, when processed with enough elegance and time, can eventually turn around and ask how it got there. Dark matter, the universe's most enigmatic ingredient, has long been a ghost in the cosmic machine, invisible yet holding galaxies together with its gravitational grip. But what if its shadowy nature isn't just a puzzle to solve, but a relic from reality's first quantum moment? Some theorists propose that dark matter's peculiar properties aren't accidental. They're cosmic breadcrumbs, traces of how the universe collapsed from a blur of possibilities into the concrete world we know. Imagine the early universe as a quantum orchestra, every possible configuration of matter and energy playing in unison. As this superposition decohered, as probabilities crystallized into definite states, most particles snapped into the familiar laws of physics we observe today. Yet dark matter, if this theory holds, might be the exception, a holdover from that primordial haze, a substance that never fully chose its quantum state. Its refusal to interact with light, its reluctance to clump like ordinary matter, these quirks could be signs that dark matter is still entangled with the universe's original uncertainty, a whisper of the time before reality made up its mind. This idea reshapes how we interpret dark matter's distribution. The way it forms halos around galaxies, its strange tendency to avoid dense regions. These patterns might reflect quantum rules writ large, remnants of how decoherence unfolded across the cosmos. Just as a drop tray of silverware scatters in a way that hints at the force of the fall, dark matter's cosmic arrangement could encode the precise manner the universe transitioned from quantum potential to classical reality. Some models even suggest dark matter particles could be quantum fossils, their wave functions frozen mid-collapse, preserving superposition-like properties on galactic scales. The implications ripple further. If dark matter is indeed a relic of decoherence, it might still be entangled with other hidden sectors of reality, parallel quantum branches that branched away during the Big Bang. This could explain why dark matter seems so aloof. It's not ignoring the rest of the universe, but subtly influenced by dimensions or forces we can't perceive. Future experiments hunting for dark matter's faint interactions might not just find a new particle, but stumble upon evidence that our universe's collapse was messier than we thought, leaving threads still loosely tied to other quantum possibilities. Critics argue this stretches an already mysterious phenomenon into speculative territory, yet the math reveals eerie consistencies. Quantum field theories predict that phase transitions, like the universe's shift from superposition to definiteness, often leave behind topological defects, cracks in reality's fabric. Dark matter's gravitational effects align suspiciously well with where such defects might linger, like cosmic scar tissue. Even its abundance fits. Calculations suggest the right amount of unfinished quantum matter would naturally settle into the 5:1 ratio of dark to visible matter we observe today. The most tantalizing clue might lie in the cosmic web. Dark matter's filamentous structure, revealed by gravitational lensing, resembles the branching pattern seen in quantum entanglement networks. Perhaps the sprawling arcs of dark matter connecting galaxy clusters aren't just gravity's handiwork, they're the fossilized imprint of a quantum connection that once spanned the entire universe, a literal shadow of the superposition from which everything sprang. If this theory holds, dark matter isn't just a missing piece of the cosmic puzzle, it's a living archive preserving the moment reality chose its path. Every galaxy's invisible halo, every deflection of starlight, could be reminding us that the universe, for all its seeming solidity, still carries the ghost of its quantum origins. And as we inch closer to detecting dark matter directly, we might not just be uncovering a hidden component of the cosmos. We could be reading the universe's oldest memory, etched in the particles that never forgot how to blur. Neutrinos, those ghostly, nearly massless particles that slip through entire planets like they're not even there, might hold the key to one of physics' greatest mysteries, how the universe snapped out of its quantum haze and into the solid reality we know. These cosmic phantoms, born in the Big Bang's fireball, were likely the first particles to escape the primordial plasma, racing ahead of light itself as the universe cooled. But what if their role was far more profound than just cosmic spectators? Some theorists propose that neutrinos, with their unique quantum quirks, acted as the universe's first mediators, bridging the gap between the blur of superposition and the sharp edges of classical physics. Picture the early cosmos as a thick quantum fog where particles existed in every possible state at once, no definite positions, no clear trajectories. Under normal conditions, quantum systems decohere collapse into classical certainty through interaction with their environment. But in the universe's infancy, there was no environment, just an undifferentiated soup where even space-time itself was still flickering. Enter neutrinos. Unlike heavier particles which were bogged down by the dense plasma, neutrinos barely interacted with matter. They could travel vast distances without scattering, carrying quantum information from one region to another like cosmic couriers. As they streamed outward, their weak but pervasive interactions might have seeded the first irreversible measurements, creating tiny pockets of definiteness in the quantum chaos. This process, known as neutrino-mediated decoherence, could explain why the universe didn't stay stuck in superposition forever. Every time a neutrino grazed another particle, even if just barely, it nudged the system toward classicality, like a snowflake triggering an avalanche. Over time, these infinitesimal nudges added up, amplifying small fluctuations into the grand structures we see today. The cosmic microwave background's faint temperature variations, the seeds of galaxies, might even bear the fingerprints of this neutrino-driven unraveling, subtle scars left behind as the universe chose its state. But here's where it gets stranger. Neutrinos oscillate, they morph between different flavors, electron, muon, tau as they travel, a purely quantum behavior. In the early universe, this oscillation could have acted like a cosmic mixer, blending quantum states across vast distances. Imagine a symphony where each violinist plays a different tune until a conductor synchronizes them. Neutrinos might have been that conductor, their oscillations harmonizing the quantum discord into a universe capable of forming stars, planets, and us. Critics argue neutrinos are too light and weakly interacting to have wielded such influence, but supporters counter that in the extreme density of the early cosmos, even their feeble interactions would have occurred at staggering rates. Others suggest neutrinos may have partnered with another quantum phenomenon like primordial magnetic fields or gravitational waves to tip the scales. Future neutrino observatories, like the Deep Underground Neutrino Experiment, could hunt for relics of this process in the cosmic neutrino background, a faint whisper from the universe's first second. The implications are staggering. If neutrinos helped collapse the universe's quantum possibilities, they didn't just shape matter, they shaped time. every interaction that locked particles into place also cemented causality, turning the primordial maybe into the unshakable now. In this light, dark matter's elusiveness might not be a coincidence. It could be the last rebel holdout, a relic that resisted decoherence and remains quantum fuzzy to this day. Perhaps the most poetic twist, neutrinos are still with us. Trillions pass through your body every second, unseen and unfelt. If this theory holds, these phantoms aren't just leftovers from the Big Bang. They're living witnesses to the moment reality chose to be real, still humming the quantum tune they helped silence 14 billion years ago. Frank Tipler's omega point theory reads like science fiction until you realize it might be the universe's ultimate encore. Imagine a future so distant that time itself strains at its seams, where the collapse of reality mirrors its quantum birth in a dizzying cosmic symmetry. This isn't just poetic musing, it's a radical hypothesis suggesting that the universe's final moments could echo its first, looping back into a quantum superposition that reboots existence itself. At the heart of this idea lies Tipler's vision of the omega point, a hypothetical endpoint of cosmic evolution where intelligent life harnesses the energy of collapsing galaxies to sustain thought indefinitely as the universe contracts toward infinite density. But here's the quantum twist. Just as the Big Bang emerged from a blur of probabilities, the omega point might not herald an end, but a return to that primordial uncertainty. As space and time compress toward their limits, the distinctions between particles, forces, even observers could dissolve, forcing reality back into a state where all possible configurations exist at once. The universe wouldn't die, it would reset like a quantum computer overheating and rebooting its program. Consider the eerie parallels. In the beginning, quantum fluctuations spawned particles from nothingness. At the end, black holes evaporating into Hawking radiation could achieve the same alchemy in reverse, converting mass back into a storm of probabilities. The cosmic microwave background, that fossilized glow of the Big Bang, finds its mirror in the hypothetical heat death of maximum entropy, except entropy's victory might not be permanent. Tipler speculated that at the omega point, infinite computation could simulate every possible universe, effectively recreating the superposition from which ours arose. The circle closes, a cosmos born from quantum choice dies by returning to it. This isn't mere philosophy. Quantum mechanics allows for time-symmetric processes where the laws governing particles don't care if time runs forward or backward. If the universe's expansion reverses a big crunch rather than a cold, eternal fade, the conditions of the Big Bang could re-emerge naturally. Particles compressed beyond Planck density might regain their quantum freedom, untethered from classical physics. Even consciousness in Tipler's framework could play a role. Just as some interpretations of quantum mechanics require observers to collapse wave functions, the omega point's hyper-intelligent entities might choose which universes to manifest from the quantum foam, weaving new realities from the ashes of the old. Skeptics dismiss this as metaphysical speculation, but tantalizing mathematical threads connect it to modern physics. Conformal cyclic cosmology, loop quantum gravity, and even certain string theory models hint that the universe's birth and death could share deeper symmetries than we've imagined. The real shocker, if this cycle repeats, our universe might be one iteration in an endless sequence, each omega point birthing a new superposition that spawns another cosmos. We could be living in a cosmic Russian nesting doll where every layer whispers the same quantum truth, that endings are just beginnings waiting to be observed. The haunting beauty of this idea lies in its duality. The universe's first quantum moment wasn't a beginning, and its last won't be an end, just a pause in an infinite dance of transformation, where reality's only constant is the potential to become something new. From the holographic universe to the cosmic quantum bounce, these 30 theories aren't just wild guesses, they're the bleeding edge of our quest to understand reality's foundations. Quantum mechanics has shattered the illusion of a simple, singular Big Bang, revealing a cosmic origin story far stranger than fiction. The universe may have begun not with a bang, but with a quantum whisper, a superposition of every possible reality, a shimmering haze of might-bes and what-ifs, all collapsing into the single thread we now call home. Whether it's Penrose's cyclical eons, the participatory universe shaped by observers, or the holographic code etched on reality's edges, one thing is clear: the old model of a tidy cosmic birth is gone. In its place stands a labyrinth of possibilities where time itself is an illusion, black holes are cosmic archives, and dark matter might be the universe's forgotten quantum memory. The implications ripple far beyond cosmology. If the cosmos was born from quantum uncertainty, then randomness isn't a flaw, it's the creative force behind galaxies, stars, and us. The fine-tuned constants enabling life aren't miracles. They're statistical inevitabilities in a multiverse where every outcome plays out somewhere. Even consciousness, that flickering flame of awareness, might be more than a happy accident. It could be the universe's way of completing the circuit, folding back on itself to witness its own existence. Yet for all these dazzling ideas, the deepest mystery remains: which thread leads to the truth? Is our reality a hologram, a simulation, or one branch of an infinite quantum tree? Does time loop in cycles, or was it born from the collapse of a timeless void? The answer might lie in the next gravitational wave detection, a neutrino experiment, or a flicker of unexpected data in some future particle collider. Until then, we're left marveling at a cosmos far grander and more mysterious than we ever imagined. So here's the question that haunts every physicist, and now maybe you too: which of these theories holds the key to reality? Is it the cosmic hologram, the observer-driven Big Bang, or something even wilder we've yet to dream up? The universe isn't done revealing its secrets, and neither are we. If you're as obsessed with these mysteries as we are, hit subscribe, because this is just the beginning. The next cosmic revelation could be one video